welcome. Mr. Denne, Mr. Anders, Ms. Knappe, welcome to the stage. So in this panel, we want to speak about how a future with quantum sensors will look like and which challenges still lie ahead of us. And for that, we have invited a diverse panel from experts of different domains. First of all, we have Ms. Knappe, who holds a research professorship at the University of Colorado and has also co-founded the startup Fieldline that utilizes quantum sensors for medical applications. Furthermore, we have Mr. Denner with us, who is the former chairman of the board of management at Bosch and is also working as a spokesman for Quantum BW and is also working as strategic advisor for several startups. And last but not least, we have Jens Anders with us here today, who is the director of the Institute of Smart Sensors at the University of Stuttgart. And he's also a spokesperson for the quantum future cluster QSense that focuses on quantum sensing applications. And with that, please welcome the participants on stage. So, as I introduced, we want to talk about quantum sensors, what quantum sensors mean. And first question to Mr. Danner. Maybe some of our guests haven't even heard of what quantum sensors really mean. So maybe you can introduce to us what makes quantum sensing so special, why are we talking about it, and what applications could we look in this regard?
Okay, well, let's say if you talk to physicists, they will tell you we have done quantum physics since decades. It's nothing new to us. So the question is, of course, what's new? Well, for quantum sensing, we believe the big promise is that quantum sensors can be orders of magnitude more sensitive than conventional, for example, silicon-based MEMS sensors. If I say orders of magnitude, let's say it's at least a factor of 1,000, which means that we can measure, for example, very small fields, magnetic fields, much more sensitive than a conventional MEMS-based sensor. That's one promise. And the other promise is it's calibration free. Everybody who has done classical sensors knows that calibration of a sensor is a big issue. It's a big topic in the engineering phase, but also in high volume production. To trim sensors, to calibrate them is always, let's say, prone to errors, and it reduces sensitivity, of course. For quantum sensors, we use atomic properties that are calibration free. These are, I would say, the two main advantages that I see for quantum sensors. Of course, application fields are huge, so therefore it's, for me, not possible, let's say, to cover all of them, but I would name one that I think is most appealing for me, which are medical applications. In our body, for example, ions are moving, which means it's an electric current. An electric current is associated, we all know this from electrodynamics, with magnetic fields. So with very sensitive magnetic sensors, we can sense what's going on inside our body by outside measurements. So for example, heart beating, brain activity. So that's, for me, one of the most appealing ones.
Yeah. Sounds really interesting how a future with that could look like. Maybe let's dive a bit deeper into what quantum sensing actually means and the technology behind it. Maybe Ms. Knappe, in your opinion, what are the most promising technologies we are currently looking at in the quantum sensing space? And maybe also what developments have we seen in recent years regarding the technology of quantum sensors?
Yeah, I think, again, the sensor space is huge, and so there's also a variety of technologies, and I think each of these technologies has their own natural space where they really shine, and there's space for a lot of different ones. And so in broader terms, I think we can put them in two categories. One is the atom sensors, and I include charged or non-charged atoms in that. And on the other side are the solid-state sensors. And then within those groups, we usually distinguish between either cold sensors or warm sensors. And I think one of the difference is definitely performance. They have their own unique set of noise parameters or sizes or things like that. But the other thing is kind of the route to commercialization. So for some of the warm sensors, they're already in the market. We have first versions of them out there. And well, maybe for some of the cold atom sensors, at least we're starting, but the path to commercialization is longer because it's a more complicated technology. And so I do think there's space for all of them, and it's important that we develop a broad portfolio because even though sometimes the path to implementation is longer, they can, again, bring another level of performance to it.
Yeah. So you mentioned the different technologies. Some of them are close to commercialization. Maybe, Mr. Anders, you can maybe elaborate a bit on the timeline of quantum sensors for different industrial applications. What are we looking at? Is it something that can be done next year, or maybe a bit more into the future?
That's a great question because it really depends on the sensor you're looking at. I mean, as Mrs. Knappe said, there's a variety of sensors, and the first sensors are on the market. There's the OPMs, these optically pumped magnetometers. You can buy them commercially. They are not scalable such that you can produce millions of them, so the price is still quite high. I would say it's a mixture of, like, there's a marathon in the background, I would say. So really, before we see fully scalable, mass manufacturable quantum sensors, that's more like 10 years plus. But there's a chance that we have first products which are semi-scalable in the range of hundreds of thousands of sensors, maybe in 5 years or so. And it now really depends. So you really have to research now in the enabling technologies to integrate those. This is microelectronic integration, photonic integration, microhybrid integration technologies in general to bring them together. And there, the different platforms have different advantages and disadvantages. For instance, when you take these tangible atoms, so something which are solids, basically like diamond, there's NV centers in diamond, which have nice properties for sensing magnetic fields. You start with a piece of diamond, and then you integrate this together with electronics, with lasers, laser sources, photonics. And this can be something that can scale up to hundreds of thousands of pieces per year maybe, but maybe not much more. So if you really want to go to, like MEMS today, to hundreds of millions per year, you maybe have to find a new material where you can co-integrate photonics and electronics. So it's a mixture of, we have something which is promising for 3 to 5 years, but there's a lot more down the road. And if we really want to have quantum sensors everywhere in our everyday life, in our smartphones and so on, this is more like a 10-year horizon, I would say.
Yeah, and that's a perfect transition to the next part. We want to talk a bit more close about it, the challenges to transfer research into real industrial applications. So as you mentioned, it can take a long time to really scale it up. And as I already mentioned, Svenja Knappe, you have co-founded the startup Fieldline that utilizes quantum sensors for brain imaging solutions. Maybe you can tell us a bit from your experience. What challenges have you encountered on your journey with your startups, and maybe also what challenges do you see generally for the commercialization of these kind of sensors?
Yeah, so our company, Fieldline, we're currently selling kind of the third version of our OPM sensor technology, specifically for brain imaging. And so we're really trying to make a medical device. And that's a challenge in itself. And so I think the challenges, though, break down into several categories. There's the technological challenge. And that is supply chain challenges, especially, as we said already, scaling up. We make about 1,000, 2,000 per year right now. We can probably go to a few tens of thousands, but then we hit a manufacturing challenge at which point we have to invest in a very different scale of fabrication technology. So I think that's one point. Working with supply chains that are not necessarily set up to supply those quantities and tight tolerances of lasers, things like that. So there's this supply chain challenge to scale up from a technology's perspective. But then at the same time, there's also the application perspective. So we're working in the brain imaging field, and we spent 10 years validating our technology over and over against the existing technologies out there. So it is educating the users in the field, because they don't care if there's quantum or non-quantum in this thing. They care what clinically is helping this new sensor technology later, and seeing that, oh, and really believing, yes, we can get better resolutions. This will be better images, and I can do things with these sensors because they're not cryogenic that I couldn't do before. I can now scan new people. I can run new paradigms. But we had to educate the users on this too, and that took a very long time. So I think it is both of these sides, but it also needs that ecosystem between the users and the sensor manufacturers to then develop the technology further and actually make it successful in the field. And so I think it's not enough that we bring a new technology. It really is important that we have this other end. And that could also then be, and so if you do magnetic sensing, you pretty much work into denoising, because everything's magnetic. So you pretty much pick up all this noise. How do we, again, now take advantage of these new sensors? And so the whole software side comes into it, embedded in systems that can take advantage of it. So it's a very broad challenge, I would say, and we as technology makers can't solve all of them ourselves.
Yeah. Yeah, so you mentioned the challenge to really industrialize, scale up from numbers with like 1,000 units of your product to higher numbers where you can have really broad applications. So maybe Mr. Danner, from your perspective, what is needed to really commercialize, or let's better say industrialize, quantum sensors? And also what support measures are needed? How do we have to see these quantum sensing technologies to really get them into our industry and applications?
Well, I think to answer the question, we first have to be clear about the challenges. You mentioned already several ones. Maybe I can start from there. What we, I think, now have to do is to bring technology that is working in the lab out of the lab and put it into production. So really making a product that can be sold. And this is, of course, then much more than what physicists do in the lab. So we need an interdisciplinary approach. We need engineering, for example, microelectronics, integrated optics, and so on and so forth. So a lot of different expertise in order to make really then a quantum sensor saleable. If I say out of the lab to a product, what do I mean? First of all, dramatically reducing the size. Today's sensors are too big. Second is they are far too expensive, so dramatically reduce cost. And the third point that I can see, and you mentioned this also, is, for example, if we think about a magnetic sensor, as I said earlier, orders of magnitude more sensitive than everything that is existing today. What will be the consequence if I take it out of the magnetically shielded lab into an environment like this? The signals that we have, for example, from the electrical grid here, from your smartphones, from any train or car that's passing the building in 100 meters away, is orders of magnitude bigger than what we want to measure. And that's something we have to solve. So that's the points that I wanted to mention. The other is a non-technical one, which is to find the right applications. And let me give you a short personal story about this. When I started the development of MEMS sensors together with colleagues at Bosch many years ago, for us, the application was crystal clear. Our vision was to bring airbag into every car and the electronic stability program into every car to dramatically improve safety of vehicles, of safety of driving. So the application was clear. Precision mechanical solutions out of the military space were existing, but far too expensive. So our task was only a technical one. Can we realize these sensors in silicon and then make use of Moore's law to dramatically reduce cost by scaling as we do it in chip fabrication? Today, my view is that quantum sensors will not replace these highly sophisticated sensors, at least not in the years to come that I can overlook. Now, if we will not replace sensors that are today in earphones and smartphones everywhere, based on MEMS, well, what are the applications then? So it's difficult for somebody who is developing a quantum sensor to pick the right application, because maybe it's not in your current business field at all. Maybe it's not in automotive, and if you are an automotive supplier, well, where are you going then? Are you going into medical? You have no idea about medical devices. So this is something non-technical. Now coming to your second part of the question, what could help? The first I answered, we have to build up a quite complicated network of suppliers, partners, designing and developing, producing these new kind of sensors. Because, for example, an NV sensors in diamonds, involves laser excitation, photodiodes, integrated optics, microwaves, electronics, so a lot of different capabilities you must have in order to make a product, which means you need partners. So to build up the partnership. And my second point, right application, I really don't have an easy solution. I don't have. But obviously we need people that can think out of the box in a more maybe disruptive way and come up with new, maybe crazy ideas about new applications.
Yeah, thank you for the insights. Maybe also a support measure that can help. An example of this is the Quantum Future Cluster QCent, where Mr. Anders is the spokesperson from the University of Stuttgart. Maybe you can give some insights how QCent is able to facilitate the exchange between research institutions and also industry players, and thereby accelerating the development and adoption of quantum sensors.
That's a great question. I mean, my two co-panelists mentioned all the challenges of quantum sensing. There are many, and we try to address them by coming up with this holistic ecosystem. So we try to address the whole value chain. We have partners who specialize on really making the building blocks, the microelectronics, the photonic components, who can then serve as OEMs, as companies selling parts to system integrators. But we also have a lot of projects. Actually, we have 8 projects in total, and 6 of the 8 projects are completely market-driven. So there's a strong market pull. We try to both identify applications, and based on our initial ideas of what the applications are, we try to develop with the existing technologies custom solutions for these applications to then further develop the application itself. Because as you mentioned, the second you have a prototype that works kind of, then people come up with new ideas how you can use the prototype. People from the medical field, they start thinking about, hey, I can use it for this, but maybe there's another application of that. So there's a lot of market pull involved in there. But we also have 2 projects which are more like a technology push. So we also say we identified 2 platforms, which is diamond basically, so the NV sensor and diamond, but also some defects in silicon carbide have nice features, and we try to build an ecosystem around these 2 platforms. So in essence, we see all these challenges that were mentioned before, and we try to come up with this holistic ecosystem where like all the ingredients, all the parts in the value chain are addressed by different partners with different skill sets, including applications, including markets. Because if you don't have the markets, in the end, technology push can go into nowhere. So it's very important that we identify together the first applications, but also the ones further down the road. So it's very important that we have something in 3-5 years' time, but also then further down the road, once we are able to produce, let's say, 100 million of these sensors, it doesn't make any sense to produce them unless you can sell them. So, and that's why it's important to take all these factors into account. Yeah. And we do it with a strong collaboration of 2 universities who really do the push from the technology side, research institutions who try to bridge the gap between university research and industry, and then 18 industrial partners. And some of them are technology-oriented, and some of them are just market-oriented, really application-oriented.
Yeah. Yeah, I think that gives a good overview what challenges lie ahead of us, and also the exchange to the industry between developers. I mean, that's also something we are doing here today. Question to close the panel. I would like all of you to kind of take a bit of a look into a crystal ball. So when we look, let's say, 20 years into the future, from your point of view, what do you see as the most influential application of quantum sensors? What could be the most important application of it?
Well, I'm biased. For me, it's definitely the medical applications. Partially because I can see it's touching everybody, but like the huge impact it can have, and I can already see the novel things it enables people to do having these first sensors. As you said, it's this ecosystem of, we have the first sensors in the research market out there, so research applications are investigated, early detection of Alzheimer's, early detection of cancer, drug therapy, but that's only possible once you have these first sensors, and I think it's getting it rolling, and I can see it's rolling, and so I think I can see the huge impact, but also that it's moving in the right direction, and so for me it's going to be the biomedical ones. If it's brain or heart or cancer or muscles, that's out to be seen. I think probably in a lot of them it's going to make a difference.
I mean, obviously, biomedical is a great application field because there's a lot of value for both companies in selling these sensors, but also for society. I mean, 20 years is a long time. So I would say in biomedical, really in 10 years, we can have groundbreaking applications. My vision is in 20 years, we have really miniaturized quantum sensors, which are so small, you can maybe use them in smartphones. So for 20 years, like anything is possible, in my opinion, and then applications of that are really manifold. Maybe just to mention one thing which is very dear to my heart, because I've been working on EPR spectroscopy for the last 15 years, so trying to detect electron spins. And almost anything that has radical character in this world, which is free radicals in your body, but also defects in semiconductors, those can be detected by quantum sensors. And the second we make those sensors small enough, then really similar sensors can detect maybe cancer early in your blood, but also can detect defects in semiconductor devices to make them more reliable. So that's really something which I see 10, 15, 20 years down the road, that we detect something that is undetectable today, opening up entirely new markets. And that would be really my 15, 20 years vision.
Well, we scientists, usually we are very humble, so we hate questions like this because our honest answer would be, we don't know. So therefore, with this remark, I will not make any prediction, but I will give you my hope, let's say, my vision, what I would like to come in 20 years. And I find it very interesting. Obviously, we are in agreement without having discussed before. My vision would be, my wish would be that in 20 years, based on quantum sensors, we will be able to detect early cancer markers in our body fluids years before a tumor will develop. And therefore, these cancer cells can be easily eliminated. So that by that point of time, the word tumor will be eliminated. It will not be part of our language anymore.
Okay. Thank you all for taking the look into the future of quantum sensors here with us. And thank you all for the participation in the panel. And with that, thank you for your attention. And